All right, welcome back to 7.9. This is the last lesson for this unit, and we are going to look at a special log. We called it the natural log and the related exponential functions. Okay, so before we talk about natural log, I want to, it's not, yeah, it's a review, I guess. Let's look at this question here. It says, Mr. H has $1 and he found a bank who is willing to pay him $100, 100% annual interest rate and compounded monthly. How much would he have at the end of the year? Okay, so this is simply a compound interest question. Okay, so if we recall the formula, it was A equals to A0 or A naught times 1 plus I over n to the power of nt. Now I have $1, so that's my A naught, 1, times 1 plus the interest rate is 100%, so that's 1. Compounded monthly, so out of 12 to the power of n is 12 times 1 year. Okay? So now if we put this into a calculator, 1 plus 1 out of 12 to the power of 12 times 1. Oh, I missed it again. I'll do it again. 1 divided by 12 to the power of 12. Okay, so this end up to be 2.61. So by the end of the year, I would actually have $2.61. Now, here's the thing though. Time is continuous, right? So technically I'm collecting interest all year long, right? Every second, every tenth of a second, right? Because time is continuous. So this, I know we did it as counting period to be monthly, so we divided by 12. Now, what if n is infinitely large? So for example, what if we use the same formula, but then let's say n is, let's do a second, okay, every second. What if we collect interest every second? What would n be then? In that case, well, we have 60 minutes, and each minute is 60 seconds times 20. Okay, so hold on. 60 seconds for 60 minutes, 24 hours a day. Let's say we have 356 days in a year. Okay, so that's, oh my goodness, that's 3 million. Okay, is it 3 million? Oh, it's more than 3 million. Okay, I'm not gonna go that crazy. Okay, I'll just use 1 million. 1 million. There you go. And then 1 million. Okay, so I want to see what this actually turned out to be. Okay, so I'm going to put this into a calculator. 1 divided by a million plus 1 to the power of a million. And this is actually 2.718. So I'm just going to round to 2.72. So notice it is 11 cents difference, but this will be more. Not much, but it is still more. Now, this number is what we called, or 2.72. This is what we call a natural number, okay? Natural number E. You can find that number E on the calculator actually, okay? So this number is what we call the natural number. So notice it says the formula A equals to A naught times 1 plus I over n to the power of n to the power of nt becomes A equals A naught times e to the power of kt when n is infinitely large. Again, E is simply this value right here. And when n is infinitely large, again, that makes sense because time is continuous, right? So it would make sense to make n infinite. I know for money, I mean, if they say compound monthly, then it's going to be monthly. However, for like real life, like biology, right? Like if you're talking about the growth of bacteria, they're not going to say, oh, let's grow monthly, okay? Let me give you some interest every 2 months. No, it grows continuously, right? So it makes sense to change this equation to that for situations like those, right? When E is, when we use this equation, it means the time is continuous, right? We are compounding all the time, okay? Not just every month or every week, okay? We're doing it all the time. Okay, so again, when we do it by continuous time frame, when we have continuous time frame, then we would use this equation right here. And k represents the growth factor. If k is bigger than 0, then it's growth. If k is less than 0, then it decays, and we use this formula instead when we deal with continuous time frame. So the question is, well, then how do we figure out this value of k, right? How do we find out the growth factor? Okay, well, if you look at this formula, a equals a naught e to the power of kt, we can actually solve for k. Okay, we can take the log on both sides. So log a is equal to, oh sorry, before I log both sides, I'm going to divide both sides by a naught. So then I get e to the power of kt. Okay, and then we can take the log on both sides, 8 over a0, and this is equal to kt times log e. Okay, so now the problem is this is going to be a constant, right? Log of a value. E, remember, is a number, right? That's 2.72 approximately. So that's a number. And this is going to be a number. And I guess to solve for kt, we can divide both sides by log e. But then you notice how ugly this looks like. Okay, so what we're going to do is, well, since I can choose any log or any base when I take log, I'm just going to choose e as my base. Right? Then what happened here is then log base e of e becomes 1. So then in this case, it becomes log base e of a over a naught. And this is equal to kt. Okay, now that's it. We could solve for k by dividing both sides by t, but then that looks, messier. So this is how you can figure out the value for k, the growth factor. Now here's the thing, for base 10, we always just write log, right? We don't write base 10. So same thing, because e is used quite often, again, in biology, in real life, time is continuous, so we're going to use base e quite a bit. So again, mathematicians, we come up with a different a letter. Well, I guess we don't use a letter. We use an operation, okay, to represent log with base e. We call this the natural log, ln. Okay, so we use ln instead for log base e, and that is how you find k. Ln of a over a naught is equal to kt. Okay, so here it says this log with base e. Okay, this log with base e is what we call a natural logarithm. So instead of writing log base e, we write ln, and it's written as ln of x or pronounced as ln x. Okay, so natural logarithm simply means, it is just a special form of logarithm, and therefore it satisfies all the laws of logarithm. So all the rules that we did with logs will apply to natural log because it's just simply a special type of logarithm. Okay, so that means we can solve this equation. Again, you see this is base e. So that's the key, right? Or that's the hint. Whenever you see base e, we're going to use natural log instead, because natural log of e, or ln of e, is simply 1. So that's the good thing about using natural log when we have base e. Okay, so we can solve this equation quite easily. We can first divide both sides by 7. So 34 over 7 is equal to e to the power of 3x minus 1. Now we can log both sides. Again, instead of just taking the regular log, we're going to take the natural log of it. And the reason is because, so now I can move the 3x minus 1 to the front, is because natural log of e, ln of e, is simply 1. Okay, so this right here is simply 1. So we don't need to worry about that anymore. Therefore, we can rewrite this as ln of 34 over 7 is equal to 3x minus 1. To solve for x, I can plus 1 on both sides, and then divided by 3. That will give me my value of x. It says we want to round this to the nearest hundredth, so then we can put this into a calculator. Ln of 34 divided by 7 plus 1 divided by 3. You should get 0.86. Okay, now put the answer. Okay, so that's how you use natural log. Again, that natural log button is also on the calculator. So make sure you find that button because that's for ln. Anytime you deal with base e, you're going to use ln. Okay, here's the second example. We want to solve this equation. Same thing. We can combine the rules or can combine the logs together using the rules that we learned. So first, I'm going to move this exponent to the this coefficient to the exponent position. So ln of x squared minus ln 7 is equal to 3. Now I can combine these two ln or logs together. Simply divide them, right, like that. Okay, and now what we can do is we can change this into exponential form. Remember, this is base e, right? So it's going to be e to the power of 3 is equal to x squared over 7. Okay, again, this is simply base e. And now we can solve for x by multiplying both sides by 7. So 7e cubed is equal to x squared. And now you just need to square root both sides. Let's see. So 7 times e cubed, and then square root that. Where's the square root button? It's right here. Okay, so your answer, okay, we are rounding to the nearest hundredth, should be both positive and negative 11.86. However, just like logs, we need to plug these two values into the original equation, and notice how if we plug in the negative 11.86, and when we take natural log of that, we cannot log negative numbers. So we need to reject that answer, and the final answer would be just 11.86. Okay, example number 3, I'm going to let you try it, okay, because it's something similar to what we've done. So good luck, and I'll show you the answer in a bit. Alright, so hopefully this is what you got. You should combine the logs together. So that's, ln plus ln. So you're going to multiply the x plus 1 with x minus 2. And if you multiply them, this is what you get, x squared minus x minus 2. And on the other side, you can bring the coefficient to the exponent position. So that becomes ln of x squared. Now, because both sides are just ln of something, so then you can drop the ln. And then you get x squared minus x minus 2 equal to x squared. You can get rid of the x squared because both sides have x squares, and then you end up with negative x equals to 2, which means x is negative 2. However, again, you should always plug in the values into the original equation. Notice if you plug in negative 2 on either of them actually, or all three of them, you end up with natural log of a negative value, which we cannot do. And therefore the answer is no solution. Okay, that is the actual final answer. You got to reject that. Okay, so that is just simple long equations. Again, it's just like the ones we did earlier. It's a different base. That's all. Okay, nothing different. Nothing different. All right, example number 4. This is something different. Now E is continuous time frame. Population growth also continuous time frame. So we're gonna use natural log here. Okay, so here that means we're gonna use this formula, right? A equals A0 e to the power of kt, and that kt is equal to ln of a divided by a naught. Okay, so this is what we're gonna do. We're gonna use, and again, we are using these two formulas because time is continuous when we talk about population, right? The growth is continuous or decay. So here it says the population of Canada was 37.06 million in 2018. Canada had an annual change of 1.4% that year. Suppose the trend continues. What would be the estimated population of Canada in year 2050? Okay, so what we need to do is we need to use this formula. So we're looking for A. Given that A naught, that's the population in 2018. Times e to the power of k. We don't know k, but we do know year is going to be 32 years. Okay, so 32, but we don't know the value of k yet. So to find the value of k, we need to use this formula right here. Okay, so the kt, so I'll do on this side, kt is equal to the natural log of a divided by a naught. Now we don't actually have a and n naught here. However, what we do know is we know that there was a change of 1.4% that year. Okay, it increases 1.4%. I should say increases. I only said annual change, but it increased by 1.4% that year, which means a divided by a naught would be 1.014, right? Because it increased by 1.4%, so it should be 1 plus 0.014, right? That's the change. Right? That's what happens when you divide the new population with the old population. It increased by 1.4%. That means when you divide the new by the old, you should get 1.014. So this is how you find k. Now this is 1.4% increase that year, which means the time frame in that case is 1. Right? So k times 1 is equal to ln of 1.014. Therefore, k is equal to ln of 1.014. Okay, so that's our value of k. So then we can put this in here, e to the power of ln of 1.014 times the value of t. So 2050, that's 32 years later. So I'm going to put 32 there. Okay, so again, from 2018 to 2050, that's 32 years. So now I can just put this value or these values into the calculator. You should be able to get, let's see, ln 1.014 times 32, and then e to that power, and then times 37.06. You should end up with 57.83. Let me just round to nearest 100th. 57.83 million. Okay, so in 2050, if this growth continues, this trend continues, that's how many people there will be in Canada. Okay. Part B says, in what year will Canada reach 50 million in population? Well, so same things, all right? This is now our A, because that's the goal. We want to reach 50 million. In 2018, we had 37.06 million. E to the power of ln. The k value doesn't change. Again, we're assuming that the trend continues, and we're solving for t now. Okay, so we can solve this. This is simply an exponential equation. We can divide both sides by 37.06. This is equal to e to the power of ln, 1.014 t. Now we can log both sides. Again, because we're dealing with base e, we're going to natural log both sides. So it's going to be ln of 50 divided by 37.06 equals ln of 1.014 times t times ln of e. Remember, ln of e is simply just 1, so that we don't really need to worry about that. So your final answer is going to be ln of 50 divided by 37.06 divided by ln of 1.014 equals to t. Put this into a calculator. All right, here we go again. Ln of 50 divided by 37.06 divided by ln of 1.014. This is going to take 21.5 years. Okay, so I'm going to say 22 years, which means starting from 2018, if you add 22 years, it's going to be 2040. So in year 2040, Canada will reach the population of 50 million based on the growth in that year, okay, and assuming the trend continues. Okay, so that is it for this unit. Wow, it's a long unit, and it's pretty difficult, I think. It's a lot of things, a lot of rules. Logs is something that we have not seen in the past. So let me know if you need help. Otherwise, good luck with your questions, and I'll see you next unit. See ya.